So welcome to this lecture. So I assume for some of you all of this is known. And for some of you I might use too much. So I apologize. If I'm not talking clearly or something is not clear, please of course stop me. The whole point is to communicate sort of information. Okay, so as the title sort of says it all, I'm going to try to talk about the relation, well, many relations of course, but some relations between artificial intelligence or machine learning and physics. Okay, and these relations have been around for a very long time, and they lie at the core of machine learning. Okay, so essentially, there are many things that machine learning does, but in essence, what it tries to do is to try to predict what the user should do, or more generally to find some patterns in data. The data can be very, very general. It can be that you have text, the data can be measurements people do, the data can be that you play games and tries to learn what are the optimal moves that should be done in games. It's very, very general. In fact, practically for any possible endeavor that we do, we could try to have a machine emulate what we do, and if a task is sort of simple, then it might actually surpass us quite easily, and also if it's quite complicated, as we learned in recent years, it might surpass us. Okay? Now, many of the ideas that underlie machine learning, as I mentioned earlier, a few moments ago, had their genesis in physics, and that's also apparent in many of the names that various machine learning algorithms actually have, like, for instance, Boltzmann machines. So I guess many of you are familiar with Boltzmann distributions, and Ludwig Boltzmann, who was Austrian, and he was born in Vienna and died in Italy, and he was a pioneer. He was not believed that people didn't believe him at the time. They actually mocked him for his ideas involving atoms, but he was of course correct. He didn't know that, and he was actually quite depressed at the time that people didn't believe him and so on. But at any rate, the distribution that he found underlies, of course, much of physics, and also it's used a lot in machine learning. And some of the ideas are used in machine learning. Okay, and also many things that we use to measure how well a machine does in predicting certain things involve fundamentally what are known as entropies. So many of you, of course, know what entropies are. Some of you might not know. Okay, but entropies appear, of course, in physics. They also appear in statistics, in mathematics, and learning. I mean, when we see how well a machine does it, one of the metrics we use, as I mentioned, is basically information theory metrics involving largely entropies. Okay. Now, as you know, last year the Nobel Prize was awarded to two physicists. So this is the first time. So I have a computer scientist friend who was surprised. She said she didn't know that physicists, that computer scientists can actually get Nobel Prizes. So this was a bit of a surprise for some people, but nonetheless, it's very well deserved because, of course, many of these ideas were pioneered by physicists. And these are two of them, of course, as I mentioned, there have been many, but these are two really the pioneers that sort of launched it. I mean, so John Hoffield is, of course, one of them. And this is, who was originally a physicist. He actually originally was working in condensed matter systems and so on. And so here this is from the description of so when you get a Nobel Prize, of course, probably none of us will unfortunately get a Nobel Prize, but when you get a Nobel Prize, there's a speech and people summarize and explain why it actually was given. And here is an excerpt from this description. So essentially, Hoffield networks, what they try to do is you have certain patterns that the machine stores, and then basically, given data, or sometimes corrupted data, it tries to find out what pattern it actually corresponds to. Okay? And it can store a large number, depending on the size of the system, a large number of patterns. And some of the ideas underlying it are related to what our physicists know as spin glasses. I will not get into that. But importantly, there's an energy function. And what the system actually does, and this is a general theme in machine learning, what the system actually does is tries to actually minimize the energy cost. So basically, as a system learns or as a system evolves to find out optimal solutions and so on, it tries to roll downhill to find solutions that might be useful. And this analogy is very apt. So you can sort of see here that there is a ball rolling downhill. And as it rolls downhill, it tries to actually find the minimum, which would correspond to a stored pattern. So you can think of, in this situation, of different valleys as corresponding to different patterns that the machine has stored in this memory. And then you evolve it, you give it a given image, and it tries to evolve to find out what pattern it really corresponds to, and it can actually correct it. Okay, so that's essentially, in a nutshell, the idea. So you can see a corrupt pattern of a J in the top. Okay, it's not a very nice J. Okay, but then you can imagine launching it up top of a hill. Unfortunately, it's hidden here, but at the top of a hill. Okay, and then it rolls down. A blue ball rolls downhill, and then when it rolls all the way downhill, and which is this valley, then you have this nice correct J that you see at the bottom right-hand side. Okay. So that's the idea. And there are many analogies people have in terms of thinking how actual human memories are stored and so on. I'm not going to get into that, but that's sort of one of the things that launched it. Another thing that launched it are actually what are called the Boltzmann machines. And as I mentioned, and as many of you know, Boltzmann distributions are at the heart of physics, statistical physics. If I could show you a movie, I would show you a movie. This is a snapshot from a movie, what you see on the left-hand side. Okay, these are particles bouncing around. Classical particles at some temperature T. Okay, and as they bounce around, hit each other and hit the walls and so on, the velocities change. But if you were at any instant of time to sample the velocities and look at the distribution, you see that you have this histogram on the right-hand side. And if you look at the average value of this histogram, if you wait for a very long amount of time, and as it would evolve in time. If it were a movie, I would show it to you. These bars would go up and down and so on. But if you were to time average that and look at the velocity distribution, you would have this nice red curve. You see this red curve appearing on the right-hand side, which is the velocity distribution of a system of particles in classical equilibrium. And that describes the Boltzmann or Maxwell-Boltzmann distribution, in this case, for the velocities of classical particles. And Boltzmann machines essentially, so in the case of Hopfield networks, basically you minimize energy to have stored patterns. So basically, given the pattern, you correct it and find what it actually corresponds to. Or if you want, somebody starts to play some music and then you recognize what the music is and you know exactly what it should correspond to, okay? Here, when we have temperature, you can actually create things. So when you have temperature, you have fluctuations. You also can try to find out what are the correct answers, of course, it's what you're after. But there's also an important parameter in Boltzmann machines, which is an effective temperature. And by changing that temperature, you can introduce fluctuations and you can make the machine creative. It's not only rolling downhill, but it can also be creative. It can be less creative, it can be more creative, it can be too creative and create nonsense, okay? Not only in Boltzmann machines, in general, okay? So we can have creativity by introducing something like a temperature that reduces fluctuations. Okay, now in general, when we have high-dimensional data sets, okay, when we have, for most applications that people use machine learning for, not all, but most, the data sets are huge, okay? So for humans, it's pretty hard and or boring to actually pore over all that mountain of data, okay? For a machine, it actually becomes, it's also, of course, very consuming, and also energy consuming, as we know. And it's a problem, it's a huge, huge problem. But it's much easier for humans. And in terms of thinking about data, so each data set that you have, no matter how large it is, you can always formally cast it as a point in some space. Like for instance, all of you have some distributions of names and heights and so on and weights. I could actually draw a point that corresponds to all 30 or 2 or whatever number it is of you here, and that would have your heights and your weights and so on, and it will be a single point high-dimensional space representing all that data that appears. Now, of course, the number of you here is not that large, but you can imagine when we really have large data sets, this can be so it's sort of nice to actually compress it all into one point. Of course, we're not cheating. We're not really compressing. I should not use that word. We're compressing in terms of having just a volume of a single point, basically a zero-dimensional volume. But that, of course, has many, many coordinates. So it's a faithful representation of the actual data, but the data actually reside in high-dimensional space. Okay? Is this clear? Now, thinking about points in high-dimensional spaces, and when we have lots of so-called, what physicists like to call, and chemists and scientists like to call, degrees of freedom, that's the natural playground for statistical physics. Statistical physics is designed to predict properties of large systems for which it's impossible, or possible in theory, but impossible in practice, to actually make calculations for a huge number of particles. Avogadro's number, or whatever number it is, in general, a large number of particles, of course, nobody can actually calculate what's going to happen. Nature calculates, of course, automatically, but of course, we cannot. Okay? But nonetheless, that analyzing gases and so on that have such astronomical number of particles is, as I mentioned, what statistical physics is for. And hence, statistical physics is really a very, very natural tool for analyzing large amounts of data. Because formally, large amounts of data are like many atoms. Okay? They have their velocities, they have locations, and so on, predictions of what's going to happen. Here is a cartoon, not mine. None of these cartoons are mine, of points in high-dimensional data space. Of course, you should think about this as a projection to the plane of points that really reside in very, very large number of dimensions. Okay? Geometry becomes quite strange in high dimensions. Things that can become very, very counterintuitive in high dimensions, and also topology can become very, very counterintuitive in high dimensions. So some of our intuition is going to be completely wrong. Okay? Some of our intuition that people thought would actually make machine learning not work as well as it does was actually grounded in what happens in low dimensions, and they didn't consider what happens in high dimensions, where some of this intuition is completely false. Now, here's a comparison between, just the cartoon comparisons you can really literally and figuratively see, between what is traditional, conventional computer scientists do, which is, of course, programming. So you have a program, and you see it at the top there. You feed it to the machine, the computer. You give it data, okay? And then the machine crunches the data following the program, steps in the program, and produces an output, which is hopefully useful for you. Okay, and that's it. And then, of course, you can write a better program to do something else, or improve a current program, and so on. That's a natural evolution. You can use programming codes and so on that you have in languages. But that's, of course, ultimately what people have done for decades. In machine learning, it's a bit different. In machine learning, the machine learns by itself. Okay? People sometimes don't know, at least in the older days, now they do. But 20 years ago, people did not know what machine learning actually means. They thought, okay, this is robots or something. The machine. So machine learning means that actually, in general, the machine on its own learns. They sometimes thought just for machines that they do something. Now they usually say, okay, we should talk and so on to do things. So in this case, as you can sort of see, you give it data, the machine. You give it the output, not always. What's shown here is what are called supervised machine learning. You have to tell it the answer. You can actually only give it raw data themselves. But in most applications, current applications, you give it data and you give it the output. Okay? And then the machine on its own learns what is the right program it should follow on its own. You only give it guidance on its own. And if you actually peer into it, it might not make sense to you. The results make sense, but what it actually does under the hood is not necessarily at all obvious. So it writes code for you, in effect. And that code, whatever it writes, this program, you can then feed into the top panel right there, and then you can generate the output that you really want to have for new data sets that you don't know the answer for. Okay, that's essentially the idea. Yeah.
So the theory is you should be able to take that machine learned device on the bottom there
and plug it into the top.
Plug in the input, and you should get the output with the program that it wrote.
Exactly. But of course, if you give it the same input, it's not useful because you already know what the output should be. The point is, you give it some data, and you give it what the answer for that data is, okay? And then you give it new data. Now you want to use it for general data. And then you take what the machine actually on its own devised, and then you put it in. You plug it, as you said, back in, channel it through. You pipe it through to the top, to use what computer scientists sometimes like to call. You pipe it through to the top panel, and then it gives you the right answer, or so you hope, for a new data set that you and the machine have not seen before. So it's a general tool, yeah.
Could you give a specific example on the second one where what you might use for data and what you might use for output?
Yeah, so I'll show some examples. I mean, the canonical cartoons people show, and I will show as well, is recognizing images, cats and dogs or digits and so on. Suppose, I mean, people, and this is not new, banks have been doing this for a very long time. You write checks and so on, and you want to look at the checks, etc. So, and many other applications. So you want the machine to be able to read handwriting, for instance. So you're not going to be able to read every individual handwriting in the world, obviously, that's too much. Even I myself cannot read my own handwriting sometimes. But you can give it lots of examples, and for the examples that you give it, and you give it the answer. You say, this character written corresponds to an A. It doesn't look like an A, but actually it's an A. And this is a 7, and this is a 9, etc., etc., etc. A large collection of examples, not infinite, obviously. Then the machine on its own learns what is what. You give it a new image, it knows, this is an 8. Okay? And then you apply it. You give it now, somebody writes something, you give it to it, and then it tells you, okay, this is what's written there, as an example. But of course, it can be much more complicated than that. The example I just gave you is one of the simplest examples. But any other questions? Yeah.
Wouldn't, in theory, you'd want to run that lower example down there many hundreds or thousands of times with different sets of data to improve your model?
Absolutely. So the more data you have in general, the better the results are. But of course, it's not so simple. But it's not so simple because so you can have rigorous results about what would happen if you have an infinite amount of data. This is, of course, a mathematical result, but you can actually prove theorems about it. Okay, and people have proven theories about it, and they prove theorems by thinking about a large collection of data sets and what happens in the limit of that number becoming infinite. So you can actually prove theorems about it. And then it can prove something called the bias variance relation and so on using that. So, but you're absolutely correct. So in principle, you could do this many, many times. In reality, of course, you can't. You're limited in what you have, both in time and other resources and so on. But in principle, you're right. Any other questions? Okay, so that's really what we're at, what it sort of is. I mean, and of course, there's also unsupervised learning, which is not shown here, in which you don't give it the output. You just give it data, and you try to give it rules to find out patterns in the data on its own. Okay, which is that's so-called unsupervised learning. And then many different variants. I'm not going to go through them, of course. So this field is not new at all. Okay, and so one of the earliest examples of it was that of playing checkers. So Arthur Samuel actually devised a program that learned to play checkers. So it could evaluate moves, it could give us different scores and so on. But actually, not only it would program it, it would tell you some numbers and what to do and so on, the next move, it would actually learn from past games, or you could also feed it games, and it would learn from the games that it actually saw what are the best moves. So it would actually, it would shortcut the need to actually do all these calculations to find out what the best move might be. Okay, so the more training it had, the more data you gave it, in terms of previous games and so on, the better it became. And it could play against itself, of course, and it became better, okay? And now, of course, I shouldn't say of course, but now checkers is a solved game. Basically, the machine can always win. It can find the optimal moves, but it was not so until maybe 30 years ago, okay? So actually, the reigning world champion actually kept beating sort of various variants of machine learning algorithms at the time. He was actually he was very sick, and unfortunately he passed away. He was a brilliant mathematician. He loved checkers, and he even said when he played once against the machine, "You regret this move," and he was right. 63 moves later, the machine actually lost. You could actually calculate so much in advance. But now, essentially, it's a solved game, as many other games, as you know quite well. So importantly, the machine on its own learns, and it improves, as you can see what's written there, with time. And the name machine learning already appears in the title of his paper from the 1950s. But we don't necessarily, as I mentioned earlier, know exactly how it works. They give it certain principles. We tell them, we want to roll downhill, we want to minimize some energy or more generally what's called a loss function and so on. But exactly how it works is still an ongoing subject of research. And different people have different ideas of how it works, and they debate about what's like, and they write papers, and they do lots of calculations with various examples and so on. But in reality, it works better in many situations than you would actually expect. But it produces results which are quite often good. Not always good. Sometimes the results are bad and people don't publish them. But sometimes it gives just nonsense. Okay, but really what it is you give it data, and the machine tries to find patterns, or more generally, guess what the answer is. But just knowing so much data, it can imitate what actually should happen and give you the right answer. Okay, it doesn't necessarily follow logic. It just sort of has so much examples in store. Okay, but it essentially recreates logic on its own if you want. Okay, but just learning by rote from examples and just interpolating in between, it tries to find out what the best results should be. Okay, so we know it works, but in many situations we don't know why, and to a large extent it's an experimental science. So usually in many of these papers that you would read in people doing AI and so on, they tell you about previous work, they tell you about their own idea and so on, then they give you results of how they tested what they have, how it works and so on. And these results, of course, are very important quite often. We really test the ideas to see how they actually work. And usually some ideas are just variants of what people had before, quite naturally, and of course, across all fields. But why it works so well, as I mentioned by now quite a few times, is not understood, and to a large extent is experiment. So we're all familiar from many, many decades ago, of course, of how our senses can improve with technology, right? So we can sort of see things that we would not be able to see otherwise, very, very far away, very, very faint. Colors we cannot really see in the spectrum, not visible to us, infrared and UV and so on, okay? We can sort of hear quote unquote sounds that we cannot hear. Dogs maybe can hear and so on and beyond, okay? So, and we can smell things that we cannot, but in principle we cannot smell. And of course now with machine learning we can sort of think things that we could not think. Of course this is an oxymoron. How can you think things that you cannot think? But you know what I mean. But basically a machine can actually give you results or suggest things that you might not on your own have thought about. Okay, and you can surpass what humans can do in playing chess and playing Go and so on by far. Okay, and you can also predict. So many of these challenges are not terribly useful. Of course, playing chess is great, but it's not terribly useful for humanity. It's a nice pastime, and it's a beautiful game. And also, St. Louis, of course, a World Chess Center, as you know, actually had the championship just now, but it's not useful in the sense of practical daily life and so on for humanity. But one of the very important problems that's been around for a very long time is that of protein folding. So you have a sequence of amino acids and you want to know how the protein folds in three-dimensional space. And the machine can predict that for you very, very accurately. It was a big jump in the accuracy that we achieved. We means humanity achieved. Okay, and now it does it very, very well, biologists, including my mother, would say it's not solved yet because it works very well, but we don't know the principles. So it's like experimental science. It gives us a result. It would fold in this way. That's great. We don't actually have to do the experiment in the lab directly. We can do it numerically, but we don't know why it actually does it. Okay. So in that sense, it's still an unsolved problem. Yeah.
Well, I'm curious about the data input because the molecular interactions of the protein and the water and the solutes is not very well understood. So what is the data that makes this work?
Yeah, so basically you can do it crystallography. And so in many situations you can give it lots and lots of results for different patterns, for different sequences. And then it knows what the results are, and then it tries to give you a prediction for a new sequence. So, but you're absolutely correct, it's a really complicated problem with lots of interactions.
It seems to me like the basic data isn't available.
It is, otherwise they couldn't check the accuracy and give it.
Thermodynamics is very, very...
It's complicated, absolutely, but there are data. Yeah. So there used to be a challenge every year, and people would have to predict what it would be, and you can sort of see the scores here on the right-hand side as a function of year, how accurate it actually became. Okay, so you can see the accuracy was quite miserable. You can sort of see all these grayscale bars on the right-hand side. It was quite miserable, and then all of a sudden there was a huge spike, okay, as you can see in these orange bars, and the accuracy now is really very large. Essentially, the problem is effectively... Sorry. The accuracy went up significantly in the very recent years. So you can see on the right-hand side, the accuracy went up by a lot. Before, as you can see, it was very poor, as you can see in these bars, the grayscale bars on the right-hand side. Yeah.
So is the data not the thermodynamics, but just the known structures?
The known structures, exactly. The known structures. So it requires a lot of work in the lab, the actual lab. It's not somebody did a calculation with everything and they got the result. It's the actual experimental result. Experimental means real experimental result, not numerical. Yeah.
What significantly changed from 2018 to 2020? Different hardware, more data? What do they attribute?
The machine learning itself. So the algorithm itself, the machine learning itself. And there are certain ideas that they used which actually turned out to be very powerful. So, which I'm not in my field, okay? But they, for instance, they're looking at if there's a particular correlation between the locations that you have of amino acids and so on. And if they were, that suggested that maybe in three-dimensional space, they actually have to be relatively close to each other as well. So there are many things that actually they used. But ultimately, it's the machine learning algorithms themselves and the actual hardware itself, the size that we have and so on, all increased. But it's not my field. I don't want to say anything incorrect. But machine learning did that. That's the important thing I want to emphasize. And it now, basically, it can predict what's going to happen very, very accurately, which is very important for drug design. That's really actually why it's really an important problem. So now, many of these machine learning algorithms and their applications rely heavily, of course, on the algorithm themselves, which by itself devises, as I explained earlier, the idea. And also, as you emphasized in your questions, the data sets themselves, and also how large the machines are, okay? So one neuron can actually do interesting things, quite non-trivial things, as it turns out, one artificial neuron. But of course, if you have more neurons, you can do more. And in essence, when you have a very large number of neurons, when the network becomes very, very large, all of a sudden you have emergent capabilities. And it can do things you didn't imagine, or maybe you did imagine, but many people did not imagine it could do earlier. So there are capabilities that emerge with larger system size, okay? Larger number of neurons, and you can apply it to larger data sets and so on, and you can get very amazing predictions. This notion of emergence when you have large systems, again, is natural in physics, chemistry, in many sciences, Okay, so something emerges when you have a large number of degrees of freedom. Okay, so you can have crystals forming, and so you can have a single atom, it has its own properties. You can put lots of them together. At low temperatures, they might form a crystal, and this crystal has emergent properties which are quite notably different from that of an individual atom that forms it. It forms it repeatedly, of course, in these unit cells, but it might have very, very different properties that many of us actually look at. Same thing for other systems and fluids and so on. So you have this notion, very, very important notion of emergence. And when we have emergent properties involving a large number of degrees of freedom, quite often what we see, not always obviously, but quite often what we see is the emergence of power laws. So for instance, there are many laws that can emerge, of course, not only power laws, but power laws are actually perhaps some of the most striking things that we can actually find universally around us, which don't really care about details. So for instance, many different systems, you cannot see it so clearly here, it's on an eye exam, of course, but many different systems, if you look at the temperature of these systems and their densities, so the vertical axis is temperature, scaled by what's known as the critical temperature. The horizontal axis is basically density, okay, divided by the critical density. There are lots of different systems here. You cannot read it, but there are lots of different systems. You use different dots and so on in different systems. And if you actually look at the curves that you have for different systems, okay, and you scale them by dividing by the critical temperature and the critical density for each one of them, they can all lie exactly on top of each other. And you see that there's something that emerges for large numbers of particles. And when you have transitions, when you go from a vapor, from a gas to the liquid, and they all basically follow nice power law forms like what you can see here at the very, very bottom. Yeah.
I'm sorry to keep on this, but
yeah.
So it doesn't ever give you back information on fundamental interactions or microscopic detail. It just finesses the fundamental interactions, right?
I mean, it depends on what you applied for. So you can actually try
You're looking at protein structure, for example.
So the machine is not following the actual microscopic.
It never reflects back to that.
It doesn't go to microscopic Hamiltonian. It doesn't start from that and starts attempts to calculate from that alone what the structure is. You basically give it data, you give it actual sequences, you give it the actual result, how it actually folds, and then you try to adjust weights and biases of neurons and so on, such that, given the actual data, initial data of what the sequence actually is, it gives you out what the three-dimensional structure is. So it doesn't try to follow the actual physics and try to minimize energies and so on, taking into account solutes and hydrophobic interactions and all of that stuff. It doesn't take that into account directly on its own and just does a calculation.
Into account, and it doesn't yield it back either.
It just gives you, it gives you the actual three-dimensional structure. So it doesn't follow microscopics, as you're saying. It gives you the structure. And that's why the protein folding problem by many people is not solved. It gives you an answer, but you don't understand why it works. You have some complicated network of lots of weights and biases and so on. You have some ideas about maybe if things are usually together, they come together with some correlation, maybe there's a correlation also in space and so on. But it doesn't give you principles of how it actually happens. It doesn't do that. Yeah. So here, also, in physics and in chemistry, you have many different systems involving lots and lots of atoms. And you cannot follow all of them. I mean, for a small number of particles you can, but a small number. For a large number of particles you cannot. You cannot follow all of them and see what they're doing. But nature shows us that actually they do obey universal properties which emerge when there's a large number of them. Even when we cannot solve it because of the curse of having a large number of particles, okay, some behaviors emerge universally independent of microscopic details. So these different systems are very, very different from one another. All these different gases and so on are very, very different, but unless they behave exactly in the same way, okay, very good reasons for that. And when we try to tease out the universality of how it happens, we apply in physics we basically look at what happens in different scales, and the same thing also appears in neural networks. We basically go from one layer to the next, to the next, to the next. So people have done some analogies of trying to understand why neural networks work so well by relating it to basic principles that appear in physics and the other sciences. So to repeat what you said, the macroscopic detail might not be important. You might have capabilities and behaviors that don't really depend on that. Okay? Here's an example of a situation in which you have emergent properties, that many of you are undoubtedly familiar with. So on the left-hand side are cartoons of, and actual results, and some at the top there, of what happens for individual atoms, okay? Whether they're quantum, as you can see in the top left there, or classical on the bottom left, like billiard balls and so on. And then if you have a large collection of them, you can stack them on into solids and so on. You can have gases, and they can have very, very different properties. The analogy I want to bring forth here is that each individual ion, or whatever we want to think about, billiard ball, atom, and so on, can conceptually correspond to an individual neuron. It has very, very interesting behaviors, maybe sometimes quite simple behaviors. When we have a large collection of them together, we have emergent behaviors, like when we have solids and gases and other systems, having a large number, Avogadro's number, or whatever number we want to think about, but a large number of particles. Okay, again, just to drive this point home, here on the left-hand side, you see a cartoon of an individual atom. It has well-defined energy levels, as you all know from high school and so on. Okay, now, if you bring now more atoms together, they can form molecules. You bring one more together, you can form solids. And the individual levels that you had for single atoms now become bands. And what you had for a single atom, energy levels for a single atom, which is a quantum system. Usually you think about quantum mechanics as being something for some tiny systems, a small number of particles, small atoms, and so on. But actually, if you take all of these atoms together and bring them in a sort of periodic fashion, then you have these levels appearing now on the big scale of entire solids. Okay, so you have emergent properties, and that gives us understanding, fundamental understanding of why we have simple metals and semiconductors and insulators and so on. That's, of course, not the topic of this talk, but just to drive home this point about emergence. Now let's go back to talking about computing and what we can actually predict when we have individual solvers and when we have many of them. This is an example that many of you might know, and many of you might not know, of course, is that of wisdom of the crowds. Does this ring a bell for some people, this term, wisdom of the crowds? So some people, of course, say it's not true. Crowds can be sort of silly and so on. But nonetheless, it is true in many regards. So suppose that you have an individual solver, okay, and it has a task to do. It has to guess something. Like, for instance, you show people this jar of jelly beans, and you ask them just to estimate, not to actually count, but just you show it to them, and they ask to estimate how many jelly beans are in the jar. So each person looks at it, okay, whatever number they give you, they just write this down. I could do the same experiment here. I'd show it to each one of you this jar of jelly beans. I would write down what each one of you would predict. I would average the result, the crowd of all of you together. And then we would have data for each individual person, okay, by prediction, what they actually guess. We could average it out, and this is an actual experiment. Okay, you could average this out. So, you know, there are many estimates of 114 people. These are the estimates that you see here, etc. You average them all out. Okay, the average is 730. What's the result? 731. So the average is actually very accurate. The results themselves are crazy. That means you can see that 250, 1,250. I mean, they fluctuate a lot. Okay, so they're huge error bars. But the mean is actually very, very accurate. So just like individual solvers, like us, each one of us would make a prediction which would most likely be wrong, the collection of all of us together would give rise to emergent behavior, which can be quite accurate and quite powerful. Okay? Is this clear? And it's not only this experiment. It's been reproduced across the board many, many times. And you can do this with your friends and so on. And if the crowd is large enough, then most likely the answer will be accurate enough. Okay? So here again, I want to push home this thing about emergence and single versus many neurons. Okay, so on the left-hand side, you have a single neuron. On the right-hand side, you have many neurons. These are actual photos. These are real photos, not some cartoons and so on. Okay? And of course, we have many neurons. We can have more complicated species. And of course, there are whales and so on, which have even bigger brains, etc. I'm not going to go into that. But now let's go back to talking about machine learning artificial neurons. So what you see here on the left-hand side is a schematic describing the initial ideas people had many, many years ago about artificial neurons. Okay? They can do useful things, sometimes surprisingly useful things, but still they're quite limited in what they can do. Like an individual solver, like an individual person trying to guess how many jelly beans are in a given jar, they might have a huge error and so on. But if you put them all together and you can form them in these layers, and there are many layers together, and there are many neurons and so on, they can form these deep neural networks, then they can actually do very useful things, and they can beat all of us in Go and chess and checkers and so on, and far beyond, and create texts that are interesting, sometimes wrong, but nonetheless interesting, and have amazing capabilities. Okay, so the top there is actual neurons and biology, but beyond that, those other cartoons, of course, are cartoons of artificial neurons. So a real neuron, of course, looks like this. I mean, this is a cartoon of that, of course. So it has inputs, it has cell body, and it shoots off a signal on the axon, and then it actually goes to the next neuron and so on. And the synapse is there, and it keeps going and so on. Okay, same cartoon by some other people and so on. But of course, this is the same general idea. You have inputs from dendrites, they go to the cell body, the cell can shoot a signal off along the axon, then it can synapse to other neurons, and the whole thing is a big collection of neurons which has emergent capabilities like all of us have. We can speak, and we can do many, many things and so on. Okay? Now, the human brain contains 10 to the 11 neurons. That's 1 to 11 zeros, okay? And of course, we can do many tasks, but of course, neurons can also do certain tasks, maybe certain motor skills and so on. People get injured sometimes, they cannot do certain things that they did before, etc. Okay, and all of these neurons can actually do things in parallel. If you cannot hear me, please let me know, okay? And here is the actual first conception of an artificial neuron. Okay, you see, I cannot see it so clearly, so I actually highlighted it for you. It was published in the Biophysics journal. So physicists can claim that the artificial neuron was actually invented by physicists, even though these two people were not physicists. Okay, McCulloch and Pitts were actually not physicists, but they published the result in the Biophysics journal. Actually, these were, of course, very important and very original people. And actually, Walter Pitts, the person that you see there on the right-hand side, he was maybe even, both were exceptionally talented. But Walter Pitts was also a bit of a special individual. So for instance, he read the Principia when he was 12, and he pointed out some mistakes. And he wrote to Russell, and Russell invited him to come to Cambridge, but he didn't come. Then he ran from home when he was 15, and he became homeless, and he attended lectures at the University of Chicago, and he corrected some errors people had, like maybe you saw this movie, Big Will Hunting and so on. Good Will Hunting. This is the 1950s. 1950s. So maybe you saw the movie Good Will Hunting, and there's a janitor there that actually solves problems. So Walter Pitts was essentially the analog, a real-life analog of that. Okay, he actually walked to a professor during his office hours to get him his paper, showed him his book. Actually, showed him some mistakes he made and just ran off. And then the professor tried feverishly to find out who that was, and then he gave him a small job and so on. So he did many different things. He never really earned a formal degree. Okay, but together the two of them came up with this neuron. And what is this neuron? The neuron tries to emulate real neurons, real biological neurons. So it has inputs, as you see there, okay, on the left-hand side, x1, x2, etc. The inputs are binary. They're yes or no, or 0 or 1, and so on. And then it has a result, like what you would have shooting along the axon, which was either on or off, 0 or 1. Okay? So it's a discrete result. Yes or no, on or off, 0 or 1, whatever you want to call it. Okay? So that's the idea. And here, the answer, the output, the y, as you see there, the red line passes through this y, can only assume 2 discrete possible values. Okay? So it's a sharp cutoff. Okay? Now, you can generalize this idea of having a sharp cutoff to situations. It's not necessarily so sharp. It's more fuzzy. And so you can have some function. This maybe looks a bit complicated and so on, but the same general cartoon. You have inputs coming from the left, okay, the x1, whatever, all these arrows coming from the left. You have, they all add together, this sigma that you see there, they all come together. They're inputted into this box that you see. The box is some function, and the box spits out a result. And the result does not have to be 0 or 1. It could be 0 or 1, but it could be anything in principle. Okay? So it could be some continuous number. Okay? So this is a continuous analog of a sharp on-off neuron that McCulloch and Pitts devised earlier. Okay? And this is actually what's used currently in modern-day neural networks, because the original one, actually, this is McCulloch-Pitts neuron would be one in which this function phi would be very, very special. Okay, it would be an on-off result. If the function phi is a continuous function, the output, then it's actually a more general one. And it's what's used currently in artificial neural networks. Okay. Now, but if I had an on-off switch, I just had one neuron with an on-off switch, and I could tune, which is not what I originally had in mind, I could tune the parameters defining that neuron. Then I could try to have a boundary between the on and the off, the yes and the no. If I give it different inputs, you see these dots here? The dots are different inputs. I give it different inputs, it would tell you whether it's yes or no. How would it do it? Effectively, it draws a line, a plane, hyperplane, and so on, in the space of data. So given all these different inputs that you have, these x's and so on, x1, x2, etc., they are points in high-dimensional space. And depending on the values of these coordinates, x1, x2, and so on, they would be either yes or no. They would be either red or blue. And there will be some plane that would separate the two things from one to the other. That's essentially what you would like to have. Yeah?
In the previous slide, we put the previous one back on.
Yeah.
The output was like a row function or some function there.
Yeah, it's a phi. It's a function phi in general. Yeah, yeah.
So how do you put those all together? I mean, is that just from one neuron, or is from all the neurons? Or?
Yeah, excellent question. So I didn't go into details. So basically what happens is that you take these individual inputs, these x's, you multiply them by these numbers, these w's, you see the w's? You add them all up together, just sum them up. Add another number, which we call a bias. And then you do this addition, that's the circle that appears, this first circle to the left of a box, you add them all up. And then that's an input to the box. So there's some function, and you take that sum, put it in the argument of that function phi that you just said, and that gives you some number. And that number is the output.
That number is what?
The output. So in the McCulloch-Pitts neuron, that number would be 0 or 1. But in current machine learning, it's actually some number that could be, in principle, anything. Usually between 0 and 1, but it could be in general anything. So if you have, coming back to what you just said, if I go into more detail, if you have these inputs, you have these x's that you see there. If equations are not so clear to you, don't worry, the equations are not terribly important here. But if it's for some of you it's maybe useful, then all the more better. You basically take these inputs, these x's, you multiply them by these numbers, these w's, you add them all up, okay? You get an answer y, and if its answer is, depending on the value of y, the answer could be yes or no, and that defines a plane. So when you have linear functions like this, and you look at when y is equal to 0, or when it's positive, when it's negative, and so on, that defines the plane in this space, and points to the left or to the right of this plane are assigned different values. So you see that you have a blue dot, you have a red dot, but you see that it's not perfect, right? You see that you have a lone red dot to the right of this green surface, right? So the plane doesn't actually doesn't do justice. And also on the other side, you have a lone blue dot, which is to the left of the plane. So it's not perfect, and that's really a problem with such simple on-off switches and so on. But nonetheless, it doesn't, for this particular cartoon, it's not terrible. It sort of does a decent job. And there are some outliers, like the ones I just mentioned, but by and large, it actually is quite accurate. The same thing can be done for digits. Okay, so you give it a collection of digits. Collection of digits merely means that you have lots and lots of pixels for each individual handwritten digit. Okay, so the simplest examples are endless data sets and so on. You have 256 different pixels, and each pixel has a particular grayscale, I apologize, value. Okay, so you have now a vector, you have a collection of numbers, and now you just go sequentially from different pixels. You write down the grayscale value, how gray it is at this point, and then this point, and this point in the image. You just go across the image and just write down what the grayscale value is. That gives you a collection of 256 numbers. So it's a big collection of numbers, it's a big vector. And now, given that vector, you want to be able to predict or to say, what is the digit you're looking at? Is it an 8? Is it a 0? Is it a 1? What is it? Okay? So you could try to come up with a plane like this that would actually tell you, is it a 1 or is it a 5? Or is it a, so you could have different planes that between different wedges of the surface of the space that you're looking at. You have here a 0 in this region between these planes and this planes and so on. And here you have a 9, and here you have an 8, and so on. So you like, if possible, it's not really possible, but if possible, you would like to make cuts with planes such that it would tell you where you have a 0, is it a 0, is it a 9, is it an 8, and so on. It turns out that actually a single neuron, as I mentioned earlier, is not bad. And in fact, if you think about it a little bit more in detail, even though we usually don't do that, we just read off what digits are, people hand us, and we write ourselves. There are certain properties that actually are quite useful. For instance, if you look at the digits that somebody draws, like an 8, okay, like the one that you saw here, and you ask yourself, if I flip this digit about its center, so here's the 8, okay, here's an 8, a figure 8, I flip what I have in the bottom to the top, and I see how much difference is there between the two of them. An 8 is pretty symmetric. If I make a flip about the horizontal line, it doesn't change that much. Of course, nobody, at least not I, writes perfect 8s. There will be a difference, but the difference will not be as large as if you would have a 6 or something else. So you can have a measure of asymmetry, how non-symmetric your digit is. You can also have a measure of how dense it is. For instance, you can sort of, if I draw some digits, like a 1, I only have points on the line, okay? Whereas if I have an 8, I have more dots. The ink and the grayscale values and so on occupy a larger fraction of space, okay? So those two numbers, basically the degree of asymmetry and the density of the digits, turns out are enough in many situations to get pretty accurate predictions of, is it a 1, is it a 5, is it a 0, etc. So for instance, here's an example of a 1 and a 5. Of course, the 5s at the bottom are not terrible. The one at the top there is a disaster, but it's supposed to be a 1, okay? And then you see that you have other ones on the right-hand side there, okay? So these are now points that are in this data space, or a feature space. So we have two axes, okay? So we have the vertical axis is a degree of symmetry. The horizontal axis is a degree of density. So the ones don't have a high density, so they appear on the left. Okay, and the symmetry is higher, of course, when we have a value of x2 which is higher. And you can sort of see that in your mind's eye that you can maybe draw a plane, a line in this case, that separates more or less, not perfectly, but more or less, the blues from the reds. Okay? So you can do that. You can try to draw lines that do that. Okay? So this is a line that's sort of, it's not optimal, obviously. Okay? So obviously there are outliers, but it's not horrible. So it allows you to make a good prediction if it's a 1 or a 5 and so on. But obviously, it's not perfect. And obviously, if you really care about what numbers you have, you write checks and so on, or whatever it is, you care about what the numbers are. You cannot afford to have mistakes like that. Okay? But a single neuron on its own is not bad. And if you think not about just only 2 features, but more features, then you can have now not just simple lines. These planes can become high dimensional. They go hyperplanes. You can have more of them, and it becomes easier to separate. So if you go to actually high dimensions, then it's easier to separate the planes along different directions, so you can actually get more accurate results in principle. Okay, so that's actually an important idea. And this is something that you cannot do in low dimensions, but if you go to high dimensions, it's easier. Many of these tasks become actually easier. But of course, they involve more numbers, because now you have to define these planes with more numbers. To define them, you have to have more coefficients that tell you exactly how they tilt along different directions and so on. Okay, now my time is almost up, even though I started a few minutes late, so maybe I'll go 5 minutes because I started late, but I'm not going to go beyond that. Now, you can actually show that, as was shown by Rosenblatt many, many years ago, that you can actually have individual, simple neuron-like artificial neurons, not exactly, but essentially, what he called the perceptron. And you can actually show that if there's a result, like if there were a plane that would separate the results correctly, of course, usually there is none. But if there were a plane that would do it correctly, you can come up with an algorithm that you can prove converges at a finite amount of time to the right answer. And he actually proved it using what some physicists here, and some engineers here, and a chemist here, every scientist here would know quite well, which is actually what we use called the Cauchy-Schwarz inequality, mathematicians and so on, Cauchy-Schwarz inequalities, which are used to prove uncertainty relations in quantum mechanics. So those uncertainty relations inequalities were actually what he used to prove a finite time convergence of his algorithm, okay? And importantly, the convergence time did not scale with system size. So it's not that you had a larger data set that you had to actually do it longer. It actually was independent of that. Now, as I mentioned earlier, the on-off switch is actually problematic. It's also problematic for learning, because usually you want to roll downhill and you want to do things continuously. In reality, what people use are other functions, not on-off, like this sigmoid function, or physicists and chemists and so on maybe would think about it as a Fermi function and so on, for occupancy that you have of electrons and fermions in general. So across different fields, these functions are quite natural. They carry different names, but essentially the same function. Okay, so the point is, this function is not 0 or 1. Okay, it goes continuously between 0 and 1. And because it's continuous, you can have a continuous slope. You can differentiate. And being able to differentiate actually allows the system to learn and make updates. That would not be possible to do in a simple way if you had discrete outputs. Now, I'm running out of time, which was what I expected. But I just want to highlight here that if you have many neurons, you have emergent power laws. So what's shown here are the accuracies that various large language models have. Okay, so this is the validation loss, how large the error is, the loss function. Okay, and this is a compute, so how much resources you actually throw in, how many operations you actually throw into it. This is a petaflop, so basically this is 10 to the 15 flops. Okay, this is a lot, of course. And you see that they all fall on this line. Okay, so you see that the x-axis is basically on the log scale. I mean, it's basically, it's with powers. 10 to the minus 6, 10 to the minus 4, and so on, okay? And the vertical axis is just a linear scale. So basically, a line here means a power law. And they all bear this power law. People have theories for why this is true, and they write papers about it, and so on. But I don't think we really understand why this is true. So we have emergent behavior, emergent power laws, and we don't know, at least many people don't know why it works so well. Okay, but we know how to, if we extend this, we know what the loss would be if we had larger networks. Okay, we could just follow this line and see how accurate things might become. So one of the things that we use a lot sort of to know how accurate our results are these loss functions I just told you, but I didn't really write them for you. If we have discrete data, then we basically use entropies quite often. And if we have continuous data, we basically use some continuous function, which is like a sum of square areas function. So I think I really have to skip here a lot because I prepared too much. Maybe I'll just, because this was asked earlier about how this actually would work, so maybe I'll just show you. So suppose that you give a system images of cats and dogs, and you ask it to predict or tell you, is it looking at a cat or looking at a dog? So here each box and each circle corresponds to an individual neuron. Okay, so the boxes are the inputs. Okay, you feed an image. Okay, we all see it's a dog, but the machine has to recognize it's a dog. We're not going to write code to tell it how to recognize it's a dog or a cat. The machine on its own should learn how to do that. So we give it images and we tell it this is a dog. In every image it says this is a cat. So what would happen is we give it an image. It has all these different pixels there, as you can see. They light up. They go to the next layer, okay, as you see there. They go to the next layer and the next layer. And at the end, there are two possible outputs. Those correspond to the probabilities that the image is a cat or the image is a dog. The two dots at the very, very end, the right-hand side, are the probabilities it's a cat or a dog. Okay, so we just feed it an image, feed it another image that tells us it's a dog. Okay, we do it the same thing for a cat, you get the point. We can also, so it learns, it basically, we minimize the loss function. The loss function adjusts the weights and biases that I've not really gone into, describing the function that you asked me about earlier for the individual neurons and so on. And then we can do the opposite. We can actually give it now, we can start from the very end. So now this network is trained and so on. Okay, and now we can say, now I want you to show me a dog. And now we go backwards to generate the dog. You see this dog is not a real dog, it has 5 legs and so on. But you can now basically, by reversing what we actually created, we can now generate things that don't exist, like this artificial dog, but of course no such dog exists. But we can create, of course, much better images that you couldn't tell so easily if it was real or fake, as you know quite well. This is also a serious problem sometimes. Okay, so I probably should end soon, or now. But the point is that in many situations we really think about high-dimensional systems as we do in physics, and many tools in physics are ideal for that. And one thing that we actually like to do is minimize the loss function. And so the way we do that is to roll downhill. So we imagine that we start at some point, we want to minimize the loss function, so we just calculate the slopes along different directions, and we just coast downhill. In low dimensions, this will not work because you can get stuck quite easily in false minima. So local minimum, okay? In high dimensions, which is what people had in mind of why we shouldn't work so well. In high dimensions, it's not true. In high dimensions, you actually have many saddle points, and you can just keep coasting and not actually get stuck so easily. And that's one of the reasons actually many of these systems work far better than you might anticipate otherwise. So let me just end maybe I'll just end on something that you might find amusing. So high dimensions are also used for embedding words. As you know, ChatGPT and other systems embed words, or generally as they're called tokens, in high dimensional space. Okay, so for instance, you give it a word, and basically it embeds it as a point in high dimensional space. This is called the embedding vector. But these vectors, if you look at what the machine actually does, they carry literal sense. For instance, if you look at what you would have for an uncle or an aunt, so these correspond to vectors in high dimensional space, and you compare it to what you have for a man or a woman, then the differences between the two vectors are quite similar. Okay? So they actually obey simple relations between them that make intuitive sense. They also make intuitive sense like this. If you look at the embedding vector that you have in high dimensions for sushi in Germany and compare it to what you would have in... okay, so you see that actually it makes sense. I mean, and the machine on its own does that. You didn't tell it to do it. It recognizes it on its own. Okay? So we go to high dimensional spaces. We means the machine. We allow it to do that. And it covers patterns that are when we look at it later on, they make sense, but it actually does it so quite naturally. Maybe we ourselves do it in our own brains. Who knows? I don't know, at least. But anyway, as you can see, high-dimensional spaces are quite useful, and I sort of end where I wanted to end because I really didn't get a chance to go through all of this stuff. It's far too much. Okay. Actually, one thing I should say that something is people taught in classes until recently was actually wrong. For instance, they taught until recently that if you have more and more complicated systems, you overfit, which is true. Usually it's true. But actually it turns out if you have enough parameters, it actually becomes better. So the accuracy goes down, and then it goes up, and then it comes back down. Nobody knows what. There are papers arguing why it goes this way and so on, but there is no universally accepted theory why it goes this way. This is a new result. And that's the end of my talk, so that's it.